Hello, this is Chad Perry, and this is my video for the first homework assignment on Chapter 11. So for the first problem here, we were given this equation for the position of a particle, and we needed to be able to find, the question was asking us to find the time, position, and velocity when the acceleration equals 0. Okay, so to start with on this problem, I started by writing down the position equation that we were given, and we know that the velocity is the derivative of our position, and so when we take the derivative of what we were given, this gives us an equation for the velocity. And then doing that one more time for acceleration, we take the derivative of our velocity equation, and that gives us our equation for the acceleration of our particle. And then in the question, we know that we want to find the acceleration when the solution when the acceleration is 0. So we take 0 and set that equal to our acceleration equation, and that gives us a quadratic equation that we can solve. And when we solve that, we get two different times, and we can kind of cancel one out because we know that negative time doesn't really make sense. And so we know that the time, which is the first part of this question, is 2/3 of a second. And then using that, we can plug that back into our position equation and our velocity equation, and that's done down here. And so when we take our 2/3 of a second and plug it into both of those, we're able to find the position and the velocity at the time we needed. And so that should answer the first question there, because we have our position, velocity, and time. Okay, so this is the second homework problem for this assignment. And in this problem, we've got this bullet here that is hitting this block. And the problem tells us a few things about what's happening. It tells us that the initial position at the beginning of the block here is 0. It gives us an initial velocity and a final position, which we had to convert into feet to be able to use it with the units we have. And then, of course, we can assume that the final velocity of the bullet will be 0 because it stops inside of this block at 4 inches. And so the first part of this question is asking us to find the initial acceleration of this bullet. And the problem gives us this here equation for velocity. But this equation has this constant k in it. And so the first thing I did was solve for that constant by using some of the conditions given in the problem. So I plugged in our initial velocity and the final velocity, and then our converted value for the final position into feet. And that gives us a value of 2,700 for k. Once we have that, we can use what we know about acceleration. So we know that acceleration is the derivative of velocity. And so we can take the derivative of our velocity equation here with respect to time. And this just goes to 0, and negative kx turns into negative kv, which is what we have here. And then we can take our velocity and plug it back in for v, which gives us this equation here. And at this point, we have everything we need to plug into our equation and find the initial acceleration of our bullet. So we plug in our value of k, our initial velocity, and our time, our initial value for x here. And that gives us an initial acceleration of 2.43 times 10 to the 6th feet per second. So for part B of this problem, we want to know the time it requires for the projectile to penetrate 3.9 inches into the medium, or this block here, which is pretty close to when it actually comes to a stop. So similar to part A, we know that velocity is the derivative of our position, so we can use that to help us. So we set this equal to our velocity equation, and then we're going to rearrange that. So we have time on one side of the equation here and our position on this side. And we know to use position on part B because when reading the problem, we're looking for the time required, and this is a distance, penetrate 3.9 inches. So that tells us we're going to need to use position. And so for our bounds of integration, we know that we're starting at a position of 0, and our end position x will be the 3.9 inches. And then our time goes from our initial time of 0 up to the time that we're actually trying to find in this problem. So we're trying to solve for this t right here. So the first step is integrating this. So when we integrate the right-hand side of this equation, this will just give us a value of t. And the left-hand side of this equation here, we have 1 over something, which will turn into a natural log. And then we have our bounds of integration here. And then it just becomes a matter of trying to solve this integral. So we have our chain rule here, which gives us the negative 1 over k. Then we apply our bounds here, which gives us this, and then plugging in our numbers from up above, right here, into our equation is right here. And then we can simplify this by using rules of logarithms down to this. And then once we solve this, we get a final value of the time is 1.3662 times 10 to the negative 3 seconds. So that's the final part of this question. Okay, so the third question we have here is a similar concept to the last problem we did. We have this boat with a ball being dropped off into the water. And we need to find out how deep this lake is and how fast the ball is going when it hits the bottom of the lake. So in this problem, I actually started by solving part B, which is the velocity of the ball. And so in this question, we were given an equation for acceleration instead of velocity. And we recognize that this acceleration equation is a function of velocity, or AV. And we know that acceleration equals the derivative of velocity, which gives us this equation here. And then we rearrange this by getting similar things on the same side of the equation. So on this side we have time by moving dt over, and on this side we take our acceleration over, so 1 over our acceleration. And then for our bounds of integration, we go from our initial time of 0 to our final time. And then similarly with the velocity, we go from our v naught up to our final velocity, which is what we're trying to find right here. So then it just becomes a matter of doing this integration. So similar to the last problem, this left-hand side will just become t after we integrate it. And then we need to integrate the right-hand side. So I plugged in our given equation of velocity in. And then integrating this, we get the natural log of our acceleration equation multiplied by a chain rule, and that's from our bounds of v naught up to v final. So then we just simply work through this integration. It takes a little while, but when we rearrange things and get rid of our natural log, we can get a final equation for our velocity, which is right here. So we know that the velocity is equal to this equation. And then looking back at the question, what it wants the speed of the ball when it hits the bottom of the lake. And we know that it takes 3 seconds for that to happen. And so we simply just plug in t equals 3 into our found equation, and that gives us our velocity when it hits the bottom of the lake. And then for part B is right here. Part A, sorry. So part A, we want the depth of the lake, which is a distance or a position. So we use this here. We know that velocity is the derivative of position. And we use our velocity equation from the second part of the problem. And similarly, we rearrange this equation and then integrate. So the left-hand side of this equation will just turn into our position, x. And then this is a little simpler integration than the last one. So we integrate this and apply our bounds. and that gives us an equation for the position. And then similar to the previous part, we know that the ball hits the bottom of the lake at a time of t equals 3. So plugging that in here, and then raising this to the power and solving this, we get a final position or a final depth of the lake of 42.046 feet. Okay, so for problem number 4 in this homework set, we have this runner here with a velocity, and we're given the equation of the velocity of the runner. And there's 3 different things we're trying to find. So the first thing we're trying to find is the distance the jogger has run when t equals 1 hour. So because this is a distance, and we're given a velocity, we know that the velocity equals the derivative of the position over time. And so similar to the previous problems, we can plug in our equation for velocity, rearrange this equation to get similar things on both sides, and then begin to integrate. So we have the integral from our time of 0 to time of t, which we know t will be 1 hour, dt, and that equals our initial position, which is 0, which is given in the problem, up to our final position, which is what we're trying to find. And so then this was kind of a difficult integration. We had to use a u sub, but the left-hand side here just becomes t, and then I multiplied the 7.5 over to make the integration a little bit easier. And then using a u sub and simplifying things and plugging in our bounds, we were able to simplify this equation here. And then I was just trying to plug in everything I could from the problem to try and simplify it and make it a little bit easier. And we know that we're trying to find the answer when t equals 1 hour. And so we plug that in for t here, and then we're trying to solve for x, our position. And so solving for that, we can find out that the position at 1 hour, or the distance he's gone, was 7.15 miles. So for part B, it says the jogger's acceleration at t equals 0. So if we're looking for the acceleration, we need to find an equation for the acceleration. And so we know that this is something we pulled out of the notes, that acceleration equals velocity times dv dx. And so similar to the other problems, we rearrange this and make it something that we can work with. So we're taking the derivative of our velocity equation that we found up above, and using that to find our acceleration that the question wants. And so when we take the derivative of this is the solution that I got, and that's part of the chain rule there. And then we just try and simplify this by multiplying things through, which gives us this equation. And then at this point, we're looking for the acceleration when t equals 0. And we know that t equals 0 when x equals 0. And so plugging that in to our equation here, we can find that the acceleration that the problem is asking for at t equals 0 is negative 275 times 10 to the negative 6 feet per second. So he was slowing down. And then part C asks the time required for the jogger to run 6 miles. And so we're going to use our equation from up above to solve part C. And we know that x equals 6 miles. And so for part C, we just need to plug in the 6 instead of 0 and solve that. And that gives us a time of 49.9 minutes for our jogger to run the 6 miles. Okay, so for problem 5 in this homework set, we're given this little diagram here of the Earth, and the radius of the Earth is big R, and then there's this particle or object here, and we're trying to find the escape velocity for this particle. or basically how fast it has to be traveling when it takes off to be able to escape the pull of Earth's gravity. And then little r is the distance from the center of the Earth to our particle. So the tricky part of this problem I found was trying to figure out the bounds of integration for us to integrate. It was a bit tricky, but to start off with, I just rewrote the equation that the problem gave us for acceleration right here. And then from our class, we know that acceleration is equal to the velocity times dv dr, or the derivative of the velocity with respect to position, where in this problem our position is a radius denoted with dr. And so the first thing that we do is we want to put like similar things on the same side of the equal sign and then integrate. And so doing that, this is what we have. And like I said, the tricky part was figuring out the bounds for our integration. But it gave us a hint here that was really helpful. So on the left-hand side of our equation, we know that the escape velocity is our initial speed when we first take off from the Earth, and that's what we're trying to find. And then our final velocity of 0, that's the point where we'll just barely be able to leave the pull of gravity from Earth and leave. So we set that equal to 0. The problem also told us that our top bound of integration on the right-hand side, we set r equal to infinity. And then our bottom bound of integration there, we know that the particle or object is starting on the surface of the Earth. And so we set our initial position there to big R, radius of the Earth, which was given right here as 3,960 miles. So then we can begin integrating this. So on the left-hand side, it's a fairly simple integration, and we just end up with this here where we have the negative escape velocity squared over 2. And then on the right-hand side, we can treat the whole numerator here as a constant and pull it out of the integral, which just leaves us this r to the negative 2 to integrate. And so I integrated that right here. And then for our bounds of integration, I plugged those in, which simplified really nicely, actually, because 1 over infinity is basically 0, so we were able to cancel that out. And then plugging in big R into that just gave us this, which actually canceled with one of the r's in this r squared here, which just left us with a gr, because the negatives canceled as well. And then so rewriting what we have left, we're left with this part right here. And then solving our equation here for the escape velocity, because that's what we actually wanted to find, gives us this simple little equation here where escape velocity equals the square root of 2 times gravity times the radius of the Earth. And then it was just a matter of plugging in the given information from the problem. So we know the radius of the Earth was given, and that gravity in feet per second squared is 32.2. And so plugging that in gives us a final escape velocity for this problem of 36.7 times 10 to the third feet per second. Okay, so this is problem number 6 in assignment 1. And at this problem, we're looking at this piece of exercise equipment here with these pulleys. So we know that this is a constrained pulley system that we're looking at. And the first thing we need to recognize is these are our variables here. The distance that this lady pulls out this rope from the exercise machine versus how high the weight B is being lifted by the pulleys. And by looking at this picture, we can create a comparison between the distance XA and YB. And we can do this because we know that the length of this rope going through the pulleys does not change. And so by looking at these pulleys here and the length, we can deduce that XA plus 3 of YB, so YB is here and XA is here, will equal the constant length of these pulleys. The next thing we notice about this problem is that the wording of the problem tells us that we have a constant acceleration, which means that we can use the equations that we learned in physics about using a constant acceleration. And so the equation we want to use for that is this one, because it does not have time in it yet. And in the beginning of the problem, we don't know anything about the time. And so at this point, we're ready to just plug into this equation using the given information from the question. So we plug that information, and then we can solve for AB, or the acceleration of the handle and the weight. So solving that, we know that AB, or the acceleration, is 6 feet per second. And that's the first part of this question. Then we can use that to find the acceleration of the handle. And all we need to do is recognize that we can take this equation here and take the derivative of it. And so our position becomes a velocity because we're taking the derivative. And because this length is a constant, once we take the derivative of a constant, it becomes 0. So that gives us an equation for velocity. And then we repeat that step by taking the derivative again. And we now have an equation for acceleration, comparing the acceleration of the handle at A to the acceleration of the weights at B. And over here we've already solved for one of those accelerations, so we can simply take that in and plug it in over here and solve this to give us the acceleration of the other part of this machine. And so that came out to negative 18 feet per second. And that's the acceleration of the handle here. It's negative because of the direction, so we can also say that is 18 feet per second to the left. And the weights here are raising at 6 feet per second. And then for part B of this question, the question wants us to find the velocity and change in position of the handle A after 5 seconds. So we can go back to our big 3 equations from Physics 1, because we know we have a constant acceleration still. And this time we want to pick an equation that has time in it. And so we chose this equation here. And then all we do is plug in what we know. So we're trying to find the velocity at A, so that's still an unknown. And then the rest of this we have found in the previous parts of the question and the 5 seconds which was given to us in the problem. So solving that, we can find that the velocity at A is 9 feet per second. And then the final thing the question wants is the change in position. So we go back again to another one of those equations from physics, and this one here has position in it. And so once again we just plug in what was given in the 5 seconds that the question gave us, and this is what we solve for up above in part A. And then just plugging that in, we can find that the position of the handle A after 5 seconds was 2.25 feet, and that is to the left of its starting position. So for problem number 7 here, we have this little parachuter guy, and the problem walks us through as he falls to the ground. So as this parachuter goes through the ground and opens his parachute, there's different stages that he goes through. And so in this problem, we had to graph each of these stages using a velocity versus time graph and a position versus time graph. And so right here is the velocity versus time graph that I created. So on the y-axis here we have velocity, and then each of the time sections that he goes through is labeled here. And then the position graph is similar, with position on the y-axis and the different time sections on the x-axis. So as we've been learning about graphical analysis, we've learned that we can relate velocity, acceleration, and position using these graphs. So for example, the area under a velocity graph is our position. And then on the other side, we can use the slope of a position graph to find velocity. And so that's some of the things we used as we were solving this problem. So the first thing we had to do was actually graph these. And so You can see here that I've used the information from the graph, or from the question, to create this graph. And we start by just labeling the different parts and drawing these graphs out to match what the problem tells us. For example, when we know that there's a constant deceleration, that tells us that the velocity is 0 during that section, so we have a straight line for the second time here. So once we have those graphs done, we can actually use them to solve the questions that the question wants. So part A of that was the time required for the parachutist to land after opening his parachute. And so what we do here is we take this velocity versus time graph and we can pull the information out from that to get that information. So what we have here is the area under this curve is equal to the position, which is what we're trying to find. And so we break it into pieces, and we're basically finding the area of each of these little sections. So for the first time, we find the area of this square plus the area of this triangle, and that is equal to x1. And so that's what this equation is here. And so we have x1 equals t1, negative t1, because it's under the x-axis, so it's a negative area, times the area of this square plus the area of this square. And then we just simply solve this, and that gives us t1. And when I did this problem, I did not convert units yet, which it probably would have been easier to do at the beginning. But because I didn't, it gave me an answer in hours, so this was the time in hours. But then I could just multiply that by 3600 to get it into seconds. So t1 was this 0.4032 seconds. And then all we had to do was repeat the same process for x2 and x3 for those positions. And so we took the area of this square and this triangle and repeated similar steps to get those 2 times. And so once we had those, all we had to do was add those 3 times together for each of these sections, and we had the total time for the parachute to land. And that's what question part A was asking. And part B was asking for the initial deceleration of the parachute. And so to solve this problem, we had to recognize that acceleration is a change in velocity over a change in time, which is basically a derivative. And so using that, we can plug in the change in velocity of our parachutist divided by the change in time. And we're looking at the first section here, so the time was t1. And then after solving that, that gives us that initial deceleration, which is 103.35 meters per second. And that's the end of this problem. Okay, so for problem number 8 here, the question gives us this equation for our position. And the question wants us to determine the magnitudes of the velocity and acceleration of the particle. And so the first thing I did was just write down the equation that was given for our position. And then we needed to recognize that the velocity is the derivative of our position. And so all we had to do for this problem was take the derivative of this equation, recognizing that we keep I, J, and K separate for the different directions because we're working in the Cartesian coordinate system. And so I recognized a couple of constants in our equation that we could use when we're taking the derivative. And then these are just the steps I took to solve that derivative to get down to the velocity. And then I cleaned that equation up a little bit here after I took the derivative. And then to find the acceleration, it was just a similar process, but it was a little more complicated derivative. We had to remember the rules for taking the derivative of sine and cosine, as well as the chain rule there. So working that through, we were able to find the derivative for acceleration as well. And when taking the derivative, you need to take the derivative of each of these pieces individually for I, J, and K. And then looking back at the problem, we recognize that the problem was actually asking for the magnitudes, not the equations. And so the rule with the magnitude is we have to square the terms, add them together, and then take the square root of those. And so doing that gave us the equations for the velocity and acceleration in terms of magnitude. Okay, so this is problem number 9, and in this problem we have this diagram here of a softball pitcher pitching to this batter, and the question wants us to determine if the pitch meets the maximum height requirement. So in the question it tells us that the max height of this pitch needs to be between 1.8 meters and 3.7 meters from the ground, and so we need to check if that's true. So looking at this problem, we can recognize that this is a projectile motion problem, because we know that once this softball pitcher lets go of the ball, the acceleration in the y direction will only be gravity down, and there will be zero acceleration in the x direction. So the first thing we needed to do was to find out what the height is here at the max height. And so looking at this, we know that at that time the velocity in the y direction will be 0. And so using one of our 3 equations for constant acceleration, we can set Vy equal to 0. And then in the rest of the equation here, we can get the component of our velocity in the y direction by taking the sine of the angle given. And then we can plug in our acceleration due to gravity, which is negative 9.81, and we can solve this to get the time that max occurred at. So once we have that time, we can go back up and find the position in the y direction at that time. So it's a similar step of just plugging those numbers back in to one of our equations. So we're trying to find Sy, and we have this equation here that we can plug the T max that we just solved for. And that's what I'm doing down here. And once we plug that in, we can find that the maximum height of this ball was 3.16 meters. And looking back at the question, we know that this value is in between 1.8 and 3.7. So yes, the height of the pitch was okay. And then for part B of this question, the question wants us to find the height of the ball as it reaches the batter. So the distance from the ground up to the height of the ball here. And so in order to do that, we know that the distance from the pitcher to the batter is 15 meters. And so we can use one of our constant acceleration equations, but this time we're going to be doing it in the x direction instead of the y direction. And so we set that final distance of 15.2 meters equal to our equation. And this is very similar to what we did before. This is the component of the velocity in the x direction, using the angle given and the velocity from the problem. And then these just end up being 0, mainly because we know that the acceleration in the x direction is 0, and the velocity at that point cancels. So then using that, we can solve for the time that it will take this ball to reach the batter. And once we know that, we can use the same equation as above, but this time plugging it into the y direction. And so this S of y will be the height off the ground at the time it reaches the batter. And so all we have to do is switch this to sine, because we're in the other direction, in the y direction, and plug in the time that we had. And so working through that on the calculator, we can determine that the height of the ball when it reaches the batter will be 0.937 meters. So problem number 10 was a little bit more complicated, and I didn't know exactly where to start on this problem, but I did notice that this is another projectile motion problem, and so we know that we can use the equations that we have for constant acceleration. And so I just started writing out some of those equations. And so this here is an equation in the x direction. And because acceleration is 0, a lot of those terms cancel out. And we're just left with this equation here. And then using the same equation in the y direction, things don't cancel out in the y direction because we have gravity is our acceleration of negative 9.81. And once we have those two, I was looking for a relationship between them so we could find what the question was asking for. And so I decided to take this top equation and solve it for our initial velocity and time, which gives us this equation here. And then we can plug that into the equation in the y direction, and that gives us this here. And then recognizing that sine over cosine is just tangent, this can simplify even more. And then once we have this equation, I could solve this for t squared, and that would give us an equation for time in terms of the x and y position of the souvenir balls that they're shooting into the stands here. So that was the first step, is just getting this relationship between the time that the ball lands and the x and y position of the ball. And then in the question, it wanted us to determine the range of values of v naught, so the initial velocity of the ball, if the balls are to land between points A and B. So basically, when we want the ball to land between, B and C on the stands here. And so we needed to do this twice. We needed to first find out the initial velocity that would get to point B, and then repeat the same step again for point C. And so at point B, looking at the problem, we can figure out the distance in the x direction to point B is this 8 meters here, plus the distance from here to here. And looking at that, it is 10 times cosine of this angle 35, which gives us a total distance from this person to B of 16.9 meters. And then we did the same process, but in the y direction. So we had 1.5 meters up, plus this relationship here, which was 10 times sine of 35. And adding those together, we get 7.2358 meters. So now we have the position of B here compared to our origin here of this person. And we can plug that into our relationship here to find the time. And so that's what I've done here, and that gives us a time of 1.305 seconds. And then we didn't want time, though, we wanted the initial velocity. But we have a simple equation here that relates velocity, time, and the x position. And so plugging in the time that we solved for, the x position, and over cosine 40 gives us an initial velocity to reach point B of 16.2 meters. And then repeating these steps for point C, we got a distance in the x direction of 21.93 meters and in the y direction of 11.25 meters. And so that was just a similar calculation. We were adding this 8 meters to the relationship of this triangle to find the total x and y distance to C from our little guy here. And then using that, our x and y position, we can plug that into our equation here to get the time that the ball would take to get to point C, which was 1.36 seconds. And then plugging that back into our equation here that we solved. So plugging in x and t, we can solve for v naught, and that gives us a time, or a velocity of 20.97 meters per second. And so that, with that information, we can solve what the question wanted us to. So this is the range of velocity. So as long as our velocity is in between 16.2 meters and 20.97 meters, we know that the ball will land between B and C, given this angle and the parameters in the question. So problem 11 here was a pretty straightforward problem. Basically we have an astronaut sitting here in this human centrifuge and he's spinning around, and we're told that he's experienced a simulated 3g forward acceleration. And so thinking about that, forward acceleration would be pointing towards the center of the centrifuge. And so that looking at our coordinate systems that we have, we know that that fits best with the normal tangent coordinate system, and that the acceleration pointing towards the center of the circle would be our normal acceleration, so I labeled that here. And then our value for rho is also given in the problem, which is he sits 5 meters from the axis of rotation, which is the distance from the center here. And then just looking at the formula, we know that the portion of the acceleration in the normal direction, or a sub n, equals our velocity squared over rho. And then all we had to do on this problem was just plug in what was given. So we take our value of 3 for our acceleration, multiply it by gravity, multiply it by rho, and then take the square root of that to find our final velocity of 12.13 meters per second. So problem 12 here is a similar concept to the last problem we were working on. So basically here we have this airplane that's making a banked turn, and the question is asking us, what is the minimum allowable radius of the turn? And so that's our value for rho. In the question, it gives us that the constant velocity is 240 meters per second, and we also know that the maximum acceleration we can have is 4g, which turns out to 39.24 meters per second squared. And so to solve this problem, all we have to do is look at this equation here that relates our acceleration, our velocity, and rho. And so rearranging that to find rho and plugging in the values of velocity and acceleration that we have, we can determine that rho equals 1,467.89 meters. And that is the smallest radius of this turn that the airplane can make and still stay within the acceleration that the question was asking about. So on this problem we have this airplane here that's making a loop, and the problem tells us that the airplane's right at the bottom of the loop where it's horizontal, and it has a horizontal velocity of 315 miles per hour. And the question is that we want to know the recorded values from this antenna dish here. And so the first thing I did on this problem was find this point right here in polar coordinates. And so we were given this triangle here and 2 of the distances, and so using inverse tangent here we could find the theta value, and the radius is just the hypotenuse of the triangle, so we could use Pythagorean theorem. And then I also had to convert the velocity given. This horizontal velocity was given to us in miles per hour, and so just doing a simple conversion we were able to convert that to feet per second. And so the first thing that the question wanted us to find was r dot and theta dot, which are the different components of the velocity. And so to find that, I drew this little sketch here that kind of helped me think that through. And then taking our total velocity, our horizontal velocity, and applying this triangle to it here, we were able to find the 2 different components that it's asking for. So theta dot, or our omega value, came out to negative 0.0924. And then in the radial direction here, our velocity for r dot came out to 370, and that's in feet per second. And then the second part of this question had to do with the acceleration. And so for this we kind of had to switch between 2 of the coordinate systems that we have. So we were given that a of t a sub t is 10 feet per second in the question. That's our tangential acceleration. And then with the formula we have, we can easily find the normal part of acceleration by taking the velocity squared over our given radius rho, which was the 1 mile or 5,280 feet. And then to find the values the question was asking for, we needed to convert these into the other coordinate system. So that's what I've done here. So I've taken the values that we had here for the tangential acceleration and the normal acceleration and converted it into something we could use to find theta double dot and r double dot. And so these are the values that I got from that conversion. And then using the other equations that we have, now that we know a sub r and a sub theta, we can use these relationships here to find r double dot and r alpha or r theta double dot. And so just plugging in what we know into these equations, we know AR, we know our position R, we know omega, which is theta dot, and we know these values here. There's R dot, which we calculated in part A. And here's omega again, which was also from part A. And then this is what we got from our triangle. And so plugging that in, we can find that for the second part of the question, R double dot is 57.9 feet per second, and theta double dot, or the second derivative, is 0.0315 radians per second squared. And this should have a squared on it as well. Okay, that's all for this question. Okay, so this is question number 14, which is the last homework question for assignment number 1. And looking at this problem, we can tell that we have another constraints pulley system. And so by looking at this problem, we can create a relationship between blocks A, B, and C. And so the first thing I did was kind of label my diagram to help me organize my thoughts. And then I looked at the diagram and created this equation here that relates YA, YB, and XC. And so because we know that the length of this rope is constant through each of the pulleys, we can look at how each of these variables change in relation to each other and create this equation. And then we can take the derivative of this to get an equation that relates the velocity of these three blocks, and then another derivative gives us the equation that relates acceleration, and the constant length of the rope just turns into 0 for those. And then the question on this problem actually gave us a lot of information. It told us that a lot of these blocks have a constant acceleration, which means that we can use our 3 equations from physics that deal with the constant acceleration. And so I looked at those equations and chose this equation here. And using the information that we were given for block B, I was able to find out what the acceleration of B is, because we're given the velocity after 2 seconds of B, and we know that the initial velocity of B is 0. And so we have everything we need to find that acceleration. And so I just wrote out everything that we were given from the problem over here on the right. And then once we had this acceleration of B, we could plug that back in to our acceleration equation. And we know that we were given the acceleration of A, so now we have 2 of these 3, and so we can plug that in and find that the acceleration of block A is 345 millimeters per second squared. And so those 2 are the answer for part A. And then for part B, the question wants us to find the initial velocities of A and C. And so this is a similar process. And so going back to our equations from physics for constant acceleration and plugging in the values that we know, and so we were told these values here for the velocity of C after 2 seconds, and the time is 2 seconds, and the acceleration of c we know is a constant 75 millimeters per second squared. And so that only leaves us with one unknown of the initial velocity of c, which is what we wanted. And so solving that, we can find out the initial velocity of c was 130 millimeters per second. And then, going back to the relationships that we created from our pulley system, we can find the velocity of a at the initial time, because we were given that the initial velocity of b is 0. And so, plugging that in, we can find this initial velocity of a is 43.3 millimeters per second, and that is up because of the wording of the problem. And then the final part of this question was part C, and it asks us to find the change in position of the slider block C after 3 seconds. So basically it wants to know how far this block C moved to the right after 3 seconds had gone by. And so going back to our constant acceleration equations, this time we want to find position, so we needed to use an equation that had position in it. And so plugging in our given values, we can find that, because at this point in the problem we've pretty much solved for most of the acceleration and velocity components for blocks A, B, and C. And so it was just a matter of plugging in the things we'd calculated or were given into this equation. And so here we can see that we were given the initial velocity of C was here, and plugging that in, we can find that the position of block C after 3 seconds was 727.5 millimeters, and that is to the right. And so that is all for this question, and that's the end of assignment number 1. Thanks.